Welcome, welcome. We are covering pedigrees. I love pedigrees. They're kind of like puzzles, so I love them. They're really kind of fun to me. Hopefully I can get you excited about them as well. So I'm working on paper. I think it's easier to sort of explain what's happening. You can see my thinking instead of just watching things magically type up on a screen. So that's why I'm working on paper with pen. I can also use different colors. Much easier than switching around fonts. So if you want to work on paper, great. If you want to just follow along on your computer, great too. All right, let's get started. On that document from the comments, we should be on pages 12 through 13 here. All right, so as a reminder, here's just a little thing about how to read pedigrees. Pedigrees are a type of family tree. We use symbols to indicate sex, female or male, and whether or not they are affected by a certain trait that we're looking at in any particular pedigree. So up here, circles indicate females, squares indicate males. If it is shaded in or colored in, these black ones here, they will be affected. They will be expressing whatever phenotypic trait that we are talking about. It'll vary from pedigree to pedigree. And if they're open or unshaded, they're unaffected. Sometimes it's dominant trait, sometimes it's a recessive trait. Siblings are placed in birth order from left to right and are labeled in Arabic numerals. Each generation is labeled with a Roman numeral. Therefore, the male exhibiting the trait in the pedigree down in pedigree below on the bottom center would be identified as III-4. So these Roman numerals indicate the generation. So I is first generation, II is the second generation, III is third generation. And then each individual of each particular generation is labeled with these regular, what we call Arabic numerals, what we're used to in our everyday. So in the first generation, we have two individuals, 1 and 2, going from left to right. In our second generation, we're going to go from left to right again. This is individual 1, 2, 3, 4, 5, 6, 7, and 8. And our third generation here, again, we're going to start over. We're only looking at each generation. This is the first individual of generation 3. This is second individual 3, 4, and 5. So the counting starts over for each generation. Just helps us be able to quickly identify each individual with their own little code of some sort. All right, so this pedigree, as it's showing over here, if it is shaded, then that individual is expressing they are affected by Huntington disease. So let's look at some of these questions. Which members of the family above are affected by Huntington's disease? Well, starting at the top here, our individual I1 has it. It is shaded. I1. All right, moving on to our second generation. We have some people here. We have I2, I3, and II7. Oh, my writing's getting smaller. And looking at our third generation, here we have just II3. III3. So all of the shaded ones are the ones I've identified here because those are the ones that have Huntington's disease. All right, how many children did individuals I1 and I2 have? So here is individuals I1 and 2, our first generation. How many children did they have? So how many are in this second generation? Well, 1, 2, 3, 4, 5, 6, 7, 8. They had 8 kids. 8 children. All right. How are individuals II2, this one right here, and II4 related? So I'll use some colors so we can figure it out. II2, so this one right here, and II4, this one right here. So how are those two related? Well, let's take a look. They're not part of the same generation. Okay, so they will have some sort of generational gap. So they can't be siblings or cousins. We're a generation apart here. Now, so let's see. II2 is a child of II1 and 2. II2 is a child of I1 and 2. So this is a child of them. Well, number II4 is also a child of I1 and 2. So II2 and II4 are siblings. They're brother and sister. Well, if II2's mother is the sister of II4, this makes their relationship uncle niece. So you can say II4 is the uncle of II2. All right, we did it. We did number 1. Let's move on to number 2. This is a much, much bigger pedigree here. So the first question it's going to ask is this trait dominant or recessive? So the shaded one, it doesn't tell us what trait we're looking at, but individuals I1 and III, III4 are all afflicted. They all have the trait, whatever it is. But it's not looking like it's very common. So let's take a look. There's going to be a bit of a puzzle going on here. This is where things are going to get fun for me, at least. So we have individuals 1 and 2 of the I generation. They're going to reproduce and have these 3 children. Well, looking here, this male has whatever trait we're looking at to be expressed. When they reproduce with I2, their 3 children do not get the trait. If it was dominant, using what we know about Mendelian genetics, if it was dominant, wouldn't all of these kids have it? So thinking about that, if all 3 of these kids do not have the trait, then that means this mom right here didn't have it either. And when she reproduced with this male, I1, their kids did not get whatever trait he had. So it must be recessive. So I'll use D for dominant. She must be at least 1 dominant, and he is homozygous recessive for it because none of his kids got it. None of his kids get it. That means they are all at least heterozygous. If mom is homozygous dominant for it, when they have kids, all of their kids will be heterozygous because they're not displaying this trait that happens to be, look at that, recessive. And if they're carrying on this trait, 3 is going to get with II4, they're going to marry there. And some of their kids have it. So that means they got at least 1 of them from dad. And if 2 of their kids are getting it, that must mean that this mom is carrying that trait as well. So she must be heterozygous to get these kids who are little d. And we don't know what I1, 2, and 5 are. They could be homozygous because there are 2 big D's for mom and dad, but they could also be heterozygous, thinking about our Punnett squares and doing heterozygous monohybrid crosses. But we know for sure that these guys here are going to be recessive because of what happened with this family right here. So it is recessive. See, this is kind of fun. It's like a mystery. All right, so we already did some of the work here. We're going to find the genotypes for all of these individuals. That's a lot. Okie doke. So we already know what I1 and 2 are. We did that work. I1 is DD, I2 is capital B, capital D. We haven't figured these ones out yet, but let's just fill in as we go here. So II1 will be heterozygous, II2 will be heterozygous, and II3 will be heterozygous. We also know what II4 is. She is heterozygous as well. We haven't figured out the rest of that second generation. What do we figure out for our third generation here? All right, so we got numbers 3 and 4 of our third generation are homozygous recessive. Look at that. We got almost half of our pedigree done here. All right, so let's move on. If we know that number 4 has to be heterozygous in order to pass on these recessive genes, that means her parents, I3 and I4, they must also have this little d, this recessive allele, to pass down to at least number 4. So that means one of them has to have at least a little d. We're not quite sure what that is just yet, but don't worry. Looking over on this side, we're not seeing any shaded shapes. So that means most likely all of these guys are not afflicted. But let's think about this as logically as we can. All right. So II4 is heterozygous. So that means they need at least one big D and one little d from mom and dad. We don't know if they are going to be heterozygous or homozygous. Most likely one of them is heterozygous, again, to get that little d, and then we can think about what these other 4 might be as well. We can make a quick Punnett square. We can just start assigning some random alleles here. Again, we're not getting too much information for the rest of these blanks, but we can hypothesize. All right, so 3 and 4, let's make a quick little Punnett square here. All right, that one. All right, so 3 and 4. In order to get at least one heterozygote there, or letter or number II4, we need at least, let's just say the dad has a big D and the mom has a little d. But the mom is not afflicted either. So she has at least one big D. Ooh, I wrote that bad. All right. Now that means there's going to be at least a little d there and a big D there. We're going to get a big D from dad. Now we need to figure out what the other D for dad is. Well, none of their children are affected by this trait. So none of them can be homozygous recessive. So this one has to be a big D there, big D, big D. So we know now what 3 and 4 are. One of them, it doesn't matter which one, is going to be big D, big D. The other one is going to be heterozygous to pass on this little d gene. Now, what can we figure out for our other 3 kids? Well, let's just go ahead and assign some of these other genotypes here. So we did that one. Let's do big D, big D, big D, little d, and big D, big D. All right, so we figured out more of the second generation here. So number 5, we gave big D, big D. Number 6, we gave heterozygous. Number 7, we did homozygous dominant. All right. Oh, I'm missing these last 2. Interesting. All right, I'll have to add those onto yours as well. More here. All right, so we have an II8, 9. Okay. And we also have a first generation 5 and the first generation 6. Or we might not even do them. We'll see. All right, so 7 and 8, they get together. All of their kids are normal as well. So we can just go ahead and, since 5 and 6 are also all normal, all of these guys over here are normal. We can just give them all homozygous dominant. And because they're all homozygous dominant, all of these guys are homozygous dominant. Great. So that means 5 and 6 are big D, big D. These second generation 8 and 9 are big D, big D. And what's left? Oh, these guys over here. We figured out first generation 3 and 4, big D, big D, big D, little d. All right, so we have 3, 1, and 2, and 5. So now we get to do some more Punnett squares. Put those together. All right, so 3 and 4, they produce 5 kids. What are the possible genotypes of 1, 2, and 5 here of our third generation? Well, let's make another Punnett square. All right, so mom and dad, we know, are heterozygous. Perfect. This will only give us 4 offspring, but we can also just kind of assign whichever we want here. So this one is big D, big D, big D, little d, big D, little d, little d, little d. So each one of these kids has an equal chance at all of these 4 different genotypes here. These two happen to get this little d, little d. So we have the options of homozygous dominant and heterozygous for the rest of these guys. So let's just say big D, big D, big D, little d, big D, little d. All right, where am I? 3, 1, we gave big D, big D. 3, 2, we gave heterozygous, and this last one we gave heterozygous as well. And there we go. We figured out. We don't know if it's 100% true because some of these could be heterozygous dominant, some of them could be homozygous dominant, but look at that. We figured out a pedigree. Kind of cool. All right, now we get to make a pedigree. All right, brown eyes are dominant eye color allele. Blue eyes are recessive. A brown-eyed woman whose father had blue eyes and whose mother had brown eyes marries a brown-eyed man whose parents are also brown-eyed. They have a son who is blue-eyed. Draw a pedigree showing all 4 grandparents, the 2 parents, and the son. Indicate each individual's possible genotypes. So in our pedigree, we first need to decide which phenotype will be shaded, brown eyes or blue eyes. Are we going to show the passing of the recessive trait, or are we going to show the passing of the dominant trait? Well, let's look here again. They get very specific about this brown-eyed woman whose father has blue eyes and mother has brown eyes. So they want to tell us, we want to make our pedigree show that she's a carrier for this blue-eye gene. So blue eyes are going to be the focus here. We're going to choose a color, choose purple. We're going to do this, shaded, and square that's shaded. All right, so they will have blue eyes. And then open ones here are going to be brown-eyed. So if they're shaded, they're going to be blue. If they're open and unshaded, they're going to be brown eyes. Now we got to make some grandparents and some parents and a kid. Well, we know the kid is blue-eyed. And we know the mom, the female, the second generation, she has brown eyes, but she's heterozygous. She gets 1 allele of blue eyes from dad and 1 allele of brown eyes from mom. And she's married to a brown-eyed man whose parents are also brown-eyed. So his parents are both brown-eyed. The kid's grandparents pass down brown-eyed genes to him. Doesn't say anything about the man's parents and their zygousness, so we can just go ahead and assume that they are homozygous for brown, and then the son is blue-eyed. Oh, but if the son is blue-eyed, we need a blue-eyed gene for the man. So one of his parents has blue eyes. All right. I love this mystery puzzle stuff. Okay, so brown eyes are dominant, blue eyes are recessive. We're trying to find the recessive blue eyes. Brown-eyed woman whose father has blue eyes. So the father will have blue eyes, and he's marrying a woman who father has blue eyes, a mother who has brown eyes. Great. And their daughter, the mom, she has brown eyes. So she's an open circle. She is going to marry a brown-eyed man, so he will also be an open circle, whose parents are also brown-eyed. I should have made this longer. Bring some light out. All right, I'll make this a little bit longer. So we have some more space here. All right, so she was going to marry this man who's brown-eyed, and his parents together they are going to have a son who has blue eyes. So this mom right here, she must be heterozygous. Let's do that in order to get this BB. This dad here will be BB, and in order to be heterozygous, this mom needs at least one big B. It doesn't matter what the second one is. All right, and this dad here, he needs to be heterozygous as well to pass on the second little b to his son. And now let's focus on figuring out what his parents are. Both of his parents are brown-eyed. Great, but he needs to get this little allele from one of them, or both of them. We kind of get to decide. So we have some options here. We need at least one little b. Doesn't matter. Actually, it doesn't matter. So we have at least one little b. We'll say it's from this dad. And then the mom, if we're getting a little b there, she can be either or doesn't really matter. So if this dad has that little allele to pass down to his son, the mom doesn't matter what she is. So there's a couple different ways we can write all this out. Many different possibilities because our description isn't quite specific enough to nail down what this female's genotype is or what this female genotype is. All right, we did it. We made our own pedigree here. Hooray! All right, I hope this was helpful. Again, if you ever need help, come to office hours, send me an email, message in classroom, and I'm more than happy to help.